Learning rules from data. As we have just seen, one way to get if-then rules is to train a decision tree and convert it to rules. Another is to learn the rules directly. Rule induction works similar to tree induction, except that rule induction does a depth-first search and generates one path rule at a time, whereas tree induction goes breadth first and generates all paths simultaneously. Rules are learned one at a time. Each rule is a conjunction of conditions on discrete or numerical attributes, as in decision trees, and these conditions are added one at a time to optimize some criterion. For example, minimize entropy. A rule is set to cover an example if the example satisfies all the conditions of the rule. Once a rule is grown and pruned, it is added to the rule base, and all the training examples covered by the rule are removed from the training set, and the process continues until enough rules are added. This is called sequential covering. There is an outer loop of adding one rule at a time to the rule base and an inner loop of adding one condition at a time to the current rule. These steps are both greedy and do not guarantee optimality. Both loops have a pruning step for better generalization. So one example of a rule induction algorithm is Reaper. This is proposed by Cohen in 1995, based on an earlier algorithm IREP. This is by Frank Kranz and Whitmer in 1994. We start with the base of two classes where we talk of positive and negative examples, then later generalize to k greater than 2 classes. Rules are added to explain positive examples such that if an instance is not covered by any rule, then it is classified as negative. So a rule, when it matches, is either correct, true positive, or it causes a false positive. The pseudocode of the outer loop of Reaper is given in figure 9.7. In Reaper, conditions are added to the rule to maximize an information gain measure used in Quinlan's 1990 FOIL algorithm. Let us say that we have rule R and R prime is the candidate rule after adding a condition. Change in gain is defined as gain of R prime R is equals to S times log base 2 of n plus prime divided by n prime minus log base 2 of n plus divided by n, where n is the number of instances that are covered by R, and n is n plus is the number of true positives in them. N prime and n plus prime are similarly defined for R prime. S is the number of true positives in R, which are still true positives in R prime. After adding the condition, in terms of information theory, the change in gain measures the reduction in bits to encode a positive instance. Conditions are added to a rule until it covers no negative example. Once a rule is grown, it is pruned back by deleting conditions in a reverse order to find the rule that maximizes the rule value metric. That is, RVM of R is equals to P minus N divided by P plus N, where P and N are the number of true and false positives respectively on the pruning set, which is 1/3 of the data, having used 2/3 as the growing set. Now figure 9.7 is the Reaper algorithm for learning rules. Once the outer loop is given, the inner loop is similar to adding nodes in a decision tree. So Reaper of parameter POS positive, NEG negative, and K, 3 parameters. First we set rule set equals to the learning rule set of pos neg, and for K times we assign rule set equals to the output of the optimized rule set of rule set, positive and negative. For the method of a learn rule set. Learn rule set with parameter positive and negative. First, we set up rule set equals to empty set. We set up DL equals to the output of DSC len of rule set and positive and negative. We repeat the following until the positive set is not empty. Then we return the rule set. So what's inside of this repeating? First, we set up rule equals to the output of learn rule of a positive and negative, and we add rule to the rule set. And we update the DL prime equals to DSC len of rule set positive negative. If DL prime is greater than DL plus 64, we prune rule set of rule set positive negative. Then we return rule set. If DL prime is less than DL, then we assign DL with DL prime. Then we delete instances covered by rule from positive and negative. Okay, so the rest methods are prune rule set method and optimize rule set method. For prune rule set method, we have input rule set, we have positive, we have negative. For each rule which is in rule set in a reverse order, we assign RL be the output of DSC len of rule set positive negative, and we assign DL prime be the output of DSC len of rule set rule pos neg, and if DL prime is less than DL, delete rule from rule set. Finally, we return rule set. For optimized rule set of rule set pos neg, for each rule which is in rule set, DL0 is the output of a DSC len of rule set pos neg. DL1 is the output of DSC len of rule set minus rule plus. Replace rule of rule set pos negative and pos negative. We assign DL2 be the value of the output of DSC len of rule set rule plus reverse rule of rule set rule pos negative pos negative. If a DL1 is the minima chosen among DL0, DL1, DL2, we delete rule from a rule set and add replace rule of rule set pos neg. And else if DL2 equals to the minima chosen among DL0, DL1 and DL2, we delete the rules from rule set and add revised rule of rule set rule positive negative. Then finally return rule set. So once a rule is grown and pruned, all positive and negative training examples covered by the rule are removed from the training set. If there are remaining positive examples, rule induction continues. In the case of noise, we may stop early, namely when a rule does not explain enough number of examples. To measure the worth of a rule, minimal description length section 4.8 is used, and that is Greenland 1995. Typically, we stop if the description of the rule is not shorter than the description of instances it explains. The description length of a rule base is the sum of the description lengths of all the rules in the rule base plus the description of instances not covered by the rule base. Reaper stops adding rules when the description length of the rule base is more than 64 bits larger than the best description length so far. So once the rule base is learned, we pass over the rules in a reverse order to see if they can be removed without increasing the description length. Rules in the rule base are also optimized. After they are learned, Reaper considers two alternatives to a rule. One, called the replacement rule, starts from an empty rule, is grown, and is then pruned. The second, called the revision rule, starts with the rule as it is grown, and is then pruned. These two are compared with the original rule, and the shortest of three is added to the rule base. This optimization of the rule base can be done k times, typically twice. When there are k greater than 2 classes, they are ordered in terms of their prior probabilities, such that C1 has the lowest prior probability and CK has the highest. Then a sequence of 2 class problems are defined such that, first, instances belonging to C1 are taken as positive examples and instances of all other classes are taken as negative examples. Then, having learned C1 and all its instances removed, it learns to separate C2 from C3, C4, and also until CK. This process is prepared until only CK remains. The empty default rule is then labeled CK so that if an instance is not covered by any rule, it will be assigned to CK. For a training set of size n, recurse complexity is big O of n times log squared of n and is an algorithm that can be used on very large training sets. The rules we learn are propositional rules, more expressive. First-order rules have variables and conditions called predicates. A predicate is a function that returns true or false depending on the value of its argument. Predicates therefore allow defining relations between the values of attributes, which cannot be done by proposition. That is proposed by Michaud in 1997. If a father of yx and the female of y, then daughter of xy. Such rules can be seen as programs in a logical programming language such as Prolog, and learning them from data is called inductive logical programming. One such algorithm is FOIL, that is proposed by Quinlan in 1990. Assigning a value to a variable is called binding. A rule matches as if there is a set of bindings to the variables existing in the training set. Learning first-order rules is similar to learning propositional rules with an outer loop of adding rules and an inner loop of adding conditions to a rule with the prunings at the end of each loop. The difference is in the inner loop, where at each step we consider one predicate to add instead of a proposition and check the increase in the performance of the rule. To calculate the performance of a rule, we consider all possible bindings of the variables, count the number of positive and negative bindings in the training set, and use, for example, equations 9.17. In this first-order case, we have predicates instead of propositions, so they should be previously defined, and the training set is a set of predicates known to be true.